Hi, my name is Ozan, and today I'm going to be doing a presentation on thermal expansion and diffusion project. For this presentation, I'm going to walk through two different physics and material science problems. The first part deals with thermal expansion and what happens when two different metal bars, one made out of iron and one made out of aluminum, are heated but prevented from expanding. The second part goes into atomic diffusion, where I use the simulation to see how atoms move under different conditions like temperature and concentration. I'll show the results I observed, compare them to the theory you learned in class, and explain why everything lines up with the expected equations. By the end, both topics connect through the idea that temperature directly affects how atoms behave. In this first problem, we start with a setup where a 1 meter iron bar and a 1 meter aluminum bar are clamped between two unmovable rigid walls. The entire system starts at 20 degrees Celsius and then the temperature is increased by 100 degrees. Normally metals expand when heated, but in this case, the rigid walls completely prevent the bars from getting longer. Since the bars want to expand but are physically unable to, they actually build up internal compressive stress instead. So the goal is to figure out what the final lengths of the bars are and how much thermal stress develops inside each metal. To understand what happens, we use the formulas for thermal expansion and thermal stress. If a bar is free to expand, the change in length is the difference in length equals to average length times average height. But in this case, the walls block that expansion, so the strain becomes zero. When you force the strain to be zero, but the material still wants to expand, the expansion gets converted into stress. As you can see, the first formula, using that formula, we can calculate the internal stress in each bar. Iron has a thermal expansion coefficient about 12 times 10 to the negative 6 and an elastic modulus around 200 gigapascals. Aluminum has a higher expansion coefficient, around 23 times 10 to the negative 6, but its modulus is much lower at about 70 gigapascals. This means iron ends up with a larger stress, about 240 megapascals, while aluminum ends up around 161 megapascals. The graph here shows how big that difference is, but the important part is both bars end up with no actual change in length because the walls force them to stay exactly 1 meter long. For the second major part of this project, I used the Festive Fusion simulation online. The simulation shows atoms moving randomly and spreading out from regions of high concentration to low concentration. I ran 3 different experiments, each one changing either the number of atoms or the temperature. The first experiment used 200 atoms on the left side at a temperature of 300 Kelvin. The second experiment reduced the number of atoms to 100, still at 300 Kelvin. And the third experiment used the full 200 atoms, but dropped the temperature all the way down to 50 Kelvin. For each experiment, I recorded how many atoms crossed the midline every half picosecond for a total of 30 picoseconds. These trials let me see how concentration gradient and temperature both affected the fusion rate. As you can see on the slide,
Greetings, everyone. This is Nick Rychek. In the first experiment, we started with 200 atoms at 300 Kelvin. The diffusion was extremely fast. As soon as the simulation began, atoms quickly moved from left side to right side. This is because the concentration gradient was very steep. The left side was packed with atoms, and the right side started empty. So the system naturally tries to spread the particles out. On top of that, the temperature was high enough that the atoms were moving around with a lot of kinetic energy. This combination of high concentration and high temperature results in a large diffusion flux. The graph here shows how stronger gradients create much larger flux values. In the second experiment, I kept the temperature the same at 300 Kelvin, but cut the number of starting atoms in half. With only 100 atoms, the diffusion behavior was still there, but it slowed down significantly compared to the 200 atom case. The reason is that the concentration gradient was weaker. Even though the temperature and kinetic energy were the same, there were fewer particles to move across the midline. This experiment confirmed that the magnitude of the concentration gradient directly affects the diffusion flux. For experiment 3, I went back to using 200 atoms, but this time I dropped the temperature drastically to 50 Kelvin. This had the biggest impact of all. The atoms were moving incredibly slow, and it took much longer for them to reach the right side. Even though the concentration gradient was strong, because there were 200 atoms on the left, the low temperature made the diffusion rate extremely small. This shows that temperature doesn't just influence movement a little bit, it has a huge effect because atomic motion comes from thermal energy. Lower temperature means the diffusion coefficient, B, becomes very small. When I compare 3 experiments, a few trends become very clear. First, the experiment with the highest temperature and highest number of atoms showed the fastest diffusion. Second, decreasing the number of atoms slowed diffusion even if the temperature stayed the same. And third, dropping the temperature made the atoms move far slower than lowering the concentration did. So temperature ended up being the most dominant factor, but both temperature and concentration gradient matter.
Hey guys, Tristan Allen here. Fick's first law tells us that diffusion flux depends on 2 things: the diffusion coefficient D and the concentration gradient dC dx. The negative sign simply means that diffusion moves from high concentration to low concentration. My experiments support this perfectly. When I cut the number of atoms from 200 to 100, I lowered the concentration gradient, and the diffusion flux decreased. When I lowered the temperature, the diffusion coefficient D changed dramatically, which also reduced the flux. So both key variables in Fick's law visibly changed results. The diffusion coefficient follows an Arrhenius-type equation. This means that temperature affects diffusion exponentially, not linearly. A small increase in temperature can cause a huge increase in D, and lowering temperature can almost freeze diffusion entirely. This is exactly what I observed when I compared 300 Kelvin to 50 Kelvin. Even though the number of atoms and the concentration gradient stayed the same between those 2 experiments, diffusion basically stalled out at the lower temperature. Even though the thermal expansion problem and the diffusion simulation seem unrelated at first, they actually connect through the same idea. Temperature directly controls atomic motion. In the bar problem, increasing the temperature makes atoms in the metal vibrate more, which is what causes expansion. But because the bars were blocked from expanding, that atomic motion turned into internal stress instead. In the diffusion experiment, increasing temperature gave the atoms more kinetic energy, which made them move and spread out faster. So in both cases, heat energy influences how atoms behave, just in different physical situations. To wrap everything up, the thermal expansion problem showed that when materials are prevented from expanding, they develop internal compressive stress. The iron bar reached about 240 megapascals, and the aluminum bar reached about 161 megapascals. In the diffusion simulations, I observed that both concentration gradient and temperature strongly influence diffusion, and my results matched the theory behind Fick's law and the Arrhenius temperature dependence of the diffusion coefficient. Overall, both parts of the assignment demonstrated how temperature affects materials at the atomic level, whether we're talking about stress in solids or the movement of atoms in gases or liquids.